Assalamualaikum warahmatullahi wabarakatuh. Today, my group will present about the Plantation Crop Mechanization AGR668. So, for the group assignment, my group choose the Paddy Crop Mechanization. So, I would like to introduce my members. My name is Luqman Hakim bin Khalid and my members Dulus Abang Anak Ungan, Muhammad Izzat bin Abdul Aziz, Faris Sifan bin Muhammad Jahari and Danish Farhan bin Zuhaimizi. So, this presentation will be presented for the Dr. Darius L. Peprian. Firstly, for the introduction, paddy or rice is a crucial staple crop for over half of the world population and is vital to Asian agriculture economies. It is harvested when grain reach maturity and have a moisture content of 20 to 25%. Advanced research and technology such as improved rice variety, precision farming technique and sustainable water management, and it aims to increase productivity and reduce environmental impact. Then, a paddy combine harvester. It's a sophisticated agriculture machine that efficiently harvests rice by performing three critical functions: there's reaping, threshing, and winnowing. So, it revolutionized rice harvesting by reducing labor and increase the productivity. Despite challenges like cost, training, and field condition, it played a crucial role in modernizing rice cultivation. Then is a paddy transplanter. A paddy transplanting machine automates the process of transplanting rice seedling from a nursery to the field, improving efficiency, reducing labor costs, and enhance the crop yield. Despite initial costs and operator training, these machines are valuable investment for moderning rice cultivation.
So next I will continue for the operation for the boats rice transplanter. So it's divided for the 4 sector, which is engine operation, movement, control mechanism and also the operational efficiency. So firstly for the engine operation, an air-cooled 4-stroke single cylinder OHV gasoline engine power the rice transplanter KNP4W and also KNP6W. The recoil starter also is used to start the engine, guaranteeing the dependable start every time. So it is also essential to do the routine engine maintenance, which include monitoring fuel level and also making sure that the automotive gasoline is unleaded is used. The 10-liter gasoline tank on both model offers enough capacity to lessen the needs for the frequent refilling stops, also by the improving the operational efficiency. So for the movement, rubber wheels with sport rims that can be raised or lowered by a hydraulic mechanism allow both transplanter to move easily. This modification is necessary to navigate various field conditions, particularly in muddy areas. This primary shift on both model allows to flexible the mobility during the planting operation with 2 forward shifting gears and also 1 reverse shifting gears. So for the control mechanism, a horizontal control mechanism is features shared by the KNP4W and also KNP6W that skips the transplanting portion horizontal and improve the planting accuracy. So furthermore, the machine head may be automatically adjusted by the transplanter to accommodate the different field circumstances and also maintain the constant performance. For the planting process, it remains accurate and efficient. Several control methods that are also essential. So for the operational efficiency, this model plantings and moving speed demonstrate how well they operate. There is a range between 0.47 to 0.65 meter per second of planting and also 0.9 to 1.64 meter per second for going in the highways. So operating efficiency for KNP4W and also KNP6W is different, which KNP4W is 0.14 to 0.26 per hectare per hour, while 6W is 0.2 to 0.36 hectare per hour. This measurement show that KNP6W more productive overall since it can cover a wider area faster and is better suited for the larger field. So I will continue for the operation for the combine harvester. So the first combine harvester is the Kubota DC60XGHK2, while the second combine harvester is Kubota DC99GHK. So firstly I will continue for the harvesting operation. So both combine harvester using the crops cut the crops by using the reaper sections. So for the first combine harvester is using the cutting width of 2000 mm, while the second combine harvester is 2182 mm. So for the threshing operation, the combine harvester separates grain from the straw. For the first combine harvester, the threshing cylinder diameter is 580mm, which is concave, while the second combine harvester is with the diameter of 670mm, which is concave. So for the grain storage operations, the clean grain is stored in the grain tank. So for the first combine harvester can store 1,400 liter, while the second combine harvester is 1,800 liter. So for the movement of maneuver operations, travel and maneuvering the combine harvester navigate the field using hydrostatic transmission, which is HST system speed. So for the first combine harvester, low is 0.98, mids 1.53, and height is 2.15 millimeter per second. While the second combine harvester, low is 0.86 meter per second, mid is 1.36 meter per second, and height is 2.10 meter per second. So I will continue for the assumption. Firstly is for the padi transplanter. Coverage is 500 hectare. Working days is around 30 days. Working hours is X hours per day. Working speed is 0.5 meter per second. For the efficiency is 75%. Power cost is 1 kilowatt is equal to 1,000 ringgit. Force is 8 kilonewton. Weight is 8 row per machine. So for the assumption, for the combine harvester, coverage is also 500 hectare. Working days is 60 days. Working hours is 11 hours per day. Speed is 1.5 meter per second. Efficiency is equal 75%. For the power cost is 1 kilowatt is equal to 1,000 ringgit. For the force is 15 kilonewton, while the width is 8 meters.
For transplanting operation, it is assumed that 30 days at 8 hours per day with a field efficiency of 75% to cover an area of 500 hectare. The first model would be the KNP4W by given the specification of the dimension of 2.14 meter with the width of 1.63 meter. Number of planting row is 4. Using a fuel gasoline with a planting row spacing of 30 cm. Planting speed is 0.5 meter per second. Operating efficiency is 0.26 hectare per hour with the engine power of 3.3 kilowatt or 4.4 horsepower. The TFC, theoretical field capacity, will be calculated by using a formula of speed times width divided by 10, which yield the 3.6 km per hour times 1.3 meter over 10, yield the value of 0.4988 hectare per hour. With the effective field efficiency by the formula of TFC times FE, yield the 0.4988 hectare per hour times 75%, yield the value of 0.3741 hectare per hour. The working width is calculated by using a formula of EFC times 10 over speed times 100 over field efficiency, yield the value of 1.63 meter. The second transplanting machine would be the Kubota KNP6W with the dimension of 2.393 meter in length and width of 2.28 meter with the number of planting row of 6, same fuel as KNPW, which is using the gasoline, planting row spacing of 30 cm with planting speed of 0.85 meter per second, same as KNP4W previously, with the operating efficiency of 0.36 hectare per hour, with the engine power of 4.1 kilowatt or 5.5 horsepower. Thus, the theoretical field capacity by using the KNP6W would be using a same formula as KNP4W, which is speed times width over 10. The 3.6 km per hour is computed from the 0.85 meter per second times 2.28 meter over 10, which yield the value of 6.9768 hectare per hour. The effective field capacity will be computed by using a formula of TFC times FE, which yield the value of 5.2326 hectare per hour. The working width by using this machine is that 22.28 meter by using a same formula as K and P for W. Therefore, the rice transplanter model KNP6W will be chosen for the transplanting operation due to its field capacity of 5.2326 hectare per hour is more than 2.0833 hectare per hour. The working width of 22.8 meter is higher than 15.43 meter, and the required power of this machine is more than the assumption value, which is 4.1 kilowatt is more than 4 kilowatt. Based on the assumption value, the required field capacity will be calculated by using a formula of covered area in hectare over hour in fields in hours, yielding a value of 2.0833 hectare per hour, which is suitable by using one machine. The required working width is using a same formula by EFC times 10 over speed times 100 over field efficiency, which yielding the value of 15.43 meter. The required power based on assumption value is that force in kilonewton times speed kilometer per hour divided by 3.6, yielding a value of 4 kilowatt.
Assalamualaikum, my name is Muhammad Izzat bin Abdul Aziz, and now I will explain on the machine capacity of the harvesting machine. So for the first machine is the DC68G harvesting tool, and which we compute the TFC, the theoretical field capacity, in which we multiply the speed, which is 4.428 kilometer per hour, times with the width, which is 2.075 divided by 10, in which we have a total TFC of 0.918 hectare per hour. And after that, we can determine the effective field capacity, which is the EFC, in which we multiply the TFC with the field efficiency, which the TFC value we multiply with 75%, which we have a total of EFC, which is 0.689 hectare per hour. And we've also determined that the working width for the machine is 2.075 meter. Okay, next for the second machine, which is the DC99G, we also do the same thing. We calculate the TFC and also EFC. So for the TFC, we get a value of 1.068 hectare per hour, and we multiply the TFC with the field efficiency, which is still 75%. We get a total value of 0.801 hectare per hour, and the working width for the machine is 2.182 meter. And after that, we've determined the required field capacity, the required working width, and also the required power for the field operations. So for the field capacity, we divide the area over the time, which we get a value of 0.758 hectare per hour. For the working width, we times the EFC with 10 and divide it with the speed, and also times it with 100 over the field efficiency. And then we get a total value of 1.872 meter. And for the required power, we simply just times the force with the speed divided by the 3.6, which we get a total of 22.5 kilowatts for power. And from the computations above, we've determined that the combined harvester model DC99G is chosen for the operation, as it meets the required field capacity, working width, and also power.
So now we go to the cost analysis, which is for Kubota DC68G harvesting 2 and Kubota combined harvester DC99G. So for the fixed cost for cost analysis for Kubota DC68G harvesting 2, for the depreciation we get 12,540 per year. Meanwhile the TSII, which is tax, shelter, insurance and interest, we get RM7,920 per year. And for the repair cost, we get 7,332.86 per year. And the total fixed cost for Kubota DC60XG, we get RM 27,000 ringgit 292.86. Meanwhile, for the Kubota DC99G, for the depreciation, we get the RM 80 ringgit 18.677 per year. And the TSII we get 11.796 per year. And for the repair cost we get 10,921.52 per year. And the total fixed cost is 41.394.52. Meanwhile, for the total operating cost, we need to find the operating cost, which is for the lubricant cost, and fuel cost and labor cost. So the total operating cost for Kubota DC60XG is RM 222.24 ringgit. And for harvester Kubota combined harvester DC99G is RM 241.44. So now we go to the cost analysis for total cost per hectare for the Kubota DC60XG. We get the total cost, which is total cost is fixed cost plus with operating cost. So total cost for Kubota DC60XG RM 28,050 ringgit, and for DC99G 41,635 ringgit. And the total cost per hectare we need to divide it by 500 and we get 56.03. And for the harvester DC99G we get 83.27. So for long term plan trading in machine, for the earliest feasible trade time, we need to multiply with 2000, which is from the table, and we get 1000 hour for the normal usage, and for the higher usage is 1500 hours. So we need assume annual use is 200 hours, and we divide it by 1000 hours divided by 200 hours, and we get 5 years. And the maximum, the high rate usage is 8 years, which is divided by 1500 divided by 200 hours. So now we go to the rice transplanter from Kubota, which is KNP. They have 4W and 6W. So this is the total fixed cost. You need to find the depreciation, the TSII and the repair cost. So the total for the KNP 4W is RM 6,434.47, and for the KNP 6W is RM 19,791.89. So this is the operating cost for the KNP 4W and 6W. So we need to find the fuel and lubricant cost and the labor cost. So the total operating cost for KNP 4W is RM 108 ringgit 42, and for the KNP 6W we get RM 109 ringgit 36 for 6W. So for the total cost, which is in cost analysis too. So the total cost is fixed cost plus with operating cost. So the total cost for KNP 4W is RM 6,542.89. Meanwhile for 6W KNP is RM 19,000 ringgit 901.25. So we need to divide by 500 hectare, which is we need assume as a farm has a 500 hectare. So the total cost per hectare is RM 13.09 per hectare. And for the 6W, RM 39 ringgit 80 per hectare. Now long-term plan for trading in machine, which is From the table, we need to go to the planter as it's a rice transplanter with 1000 least cost life and wear out life. So we need to find the normal rate usage for early feasible trade and the high rate. So we get 500 hours and 750 hours. So the earliest feasible year to trade is, we assume that the annual use is 100 hours. So 500 divided by 100, we get 5 years, and 750 hours divided by 100 hours, the maximum usage is 8 years. So
Then, lastly, for the conclusion. With this study, it evaluates the machinery for rice transplanting and harvesting operation based on the assumption and working condition. So, for the rice transplanting, it must suitable for the KNP sweet swap model. It meet the transplanting requirement with a field capacity of 5.23 to 6 hectare per hour and working width of 22.8 meter. While for the harvesting is DC99G model exceed a operational requirement with a field capacity of 0.801 hectare per hour and working width of 2.182 meter. Then, when we talk about the costing, the KNP 6 watt is a cost-effective machine for larger operation and budget conscious farmer, offering higher operational efficiency and the productivity. It can cover a 500 hectare field area and then enhance the productivity and time. Then for the combine harvester is DC99G, while higher than the DC68G. It also can improve the paddy yield quality and can operate within a 500 hectare capacity with a time period and ensure the longer operation life.